Okay, so for part 2 of 8-1 homework here, we've got questions 8 and 9 to wrap up. And hopefully 8 was a pretty straightforward one for us, but in case you want to double check anything, you certainly can. So the mass is released from rest at this position, telling us that is the amplitude. Find the maximum force, right? Find the force just as it's released. And again, that would be the maximum force, but it doesn't even ask us for that. It just asks us to find the force, which we know would be K times X. And since they give us the spring constant of 175, and the position, again, hopefully this was a pretty easy question to break up and solve here. Right, so 0.2 times 175 ends up being 35 newtons per meter. Right, so, excuse me, just newtons, not newtons per meter. We're talking force. So 35 newtons of force. There's my answer for part A. Part B, what is the maximum acceleration? Now again, the key concept here is where does the maximum acceleration happen at? And the maximum acceleration would happen at that point we just found, right? The maximum acceleration would happen at the amplitude, so it would happen right when it's first released. So for the maximum acceleration, all I have to do is take that force that I just found and divide it by the mass, right? So take my maximum force of 35 newtons and divide it by the mass, which they told me was 545 grams, so 0.545 kilograms, and that gives me my maximum acceleration to be about 64.2 meters per second squared. Right, so again, parts A and B, hopefully so far everything's all hunky-dory, right? Pretty easy. So then part C, its acceleration at x equals 0. Well, again, that's just a concept. It's not even a calculation, right? When the displacement is 0, we know that the force would be 0. So when x equals 0, we know that means the force, because force equals k times x, would be 0. And then therefore the acceleration would be 0. Right, so at that location, my acceleration is 0 meters per second squared. Part D, find its total energy. And again, whether they say it's total energy or it's total energy at a specific point doesn't make any difference. Right? To find the total energy, I'm going to find the energy somewhere, and then I'm going to use that number wherever I may need it. And so oftentimes the easiest point to find the total energy is right at that maximum displacement, because I know at that maximum displacement, it would have maximum potential energy. Right? So that's what I was trying to show here with it looked like S and then max, so it looked like smax instead of the potential energy max would equal 1/2 k times its maximum displacement, so its amplitude squared. Right, so again, this is an easy enough problem to solve once I realize that that 0.2 is its amplitude and the k that they gave me. So 1/2 times 175 newtons, or newton meters I should say, newtons per meter, and then times my displacement of 0.2 squared. Right, so 1/2 times this whole mess ends up being about 3.5 joules. So I've got my total energy, and again, that would be the total energy anywhere. So on some of the trickier questions where they ask, what's the total energy when it's at 0.05 meters? Doesn't make any difference. The total energy there would still be 3.5 joules as long as it's a simple harmonic motion. Right. So then finally part E, right, for part E, its period, and its period is just using, right, the period equation. So T equals 2 pi times the square root of m over k. So take advantage of that period equation, 2 pi times square root of my mass, which is 0.545, and then divided by my spring constant, which is 175. Right, so taking advantage of that, I find my period is about 0.35, about 0.351 seconds, so you want to take it a little bit further. Right, but again, hopefully this question pretty straightforward, pretty easy to work with. I don't think there were too many tricks on this one, but all very important things that you should be comfortable with. Okay, so question 9 here is a good way to kind of cap off the end of this first section, right? So they ask us to write the functions representing the position, velocity, and acceleration, all as a function of time. And so I'm going to start with the position function, obviously, from there. And then I'm just going to do some derivatives to help me find the other two. Now, there's other ways to get the velocity and the acceleration as well, but I'll go ahead and use the derivatives once I set up that position function. Okay, so the good news is they tell me it starts at this position and it's released from rest. And so that tells me that I am obviously using my x equals a times cosine of whatever I want the inside of this function to be. And I'm probably going to work with 2 pi ft. And the nice thing again about it starting at that position when released from rest is I know that it's starting at the amplitude. And because it's starting at the amplitude, I don't have to worry about any type of phase shift. Right? So I don't have to worry about my phi and any type of phase shift. Right? So that saves a little bit of headache, a little bit of trouble, right? For this question. But anyway, so this is the equation I'm going to work with. Obviously, I know the amplitude is the 0.08, so I've got that number to work with. The only thing that I am going to do here is I'm going to find my frequency first. Right? So they give me the mass and they give me the spring constant. And so I'm actually going to find my frequency by using the inverse of the period equation. So 1 over 2 pi radical k over m. And obviously you could have just done 2 pi over t, and you could have done this with a period instead. But I'll go ahead and just do it this way. You guys do whichever way you prefer. But plugging this in, right, 3.7 for my mass, and then calculating that, so I get the frequency to be about 1.755. Right? So again, your period is probably close to 0.5 something, right? But anyway, so I've got that number to work with. So plugging everything in for my position function, which is the first thing they wanted me to find, my amplitude again 0.08 times cosine of 2 pi times 1.755, and then t. Now I could honestly pretty much leave it here. You could also calculate it. I think the one thing I probably would do is I'm going to go ahead and leave pi in the answer, but I am going to multiply the 2 and the 1.755 since those are both just numbers. So my final answer that I'm going to go with, and again, there's nothing wrong with leaving it like this above, but I am going to go ahead and combine those numbers since I can. So cosine of 3.51 pi t. So again, I'm going to go ahead and stop with it there. For my position function, I'll stop with it there. You could go ahead and approximate 3.51 times pi, but there's no reason to do that, right? It just makes our number even less specific. So no real urgency to do that. But anyway, so I've got my position function. And again, to find your velocity function, you could say, well, velocity equals negative v max times cosine of, really it's going to be the same interior function, right? It'd be, once again, 3.51 pi of t. So you could do that and then just try and find your maximum velocity, and there's absolutely nothing wrong with doing that. However, I've gone through the work of setting up a position function. I might as well just use this and do the derivative to find the velocity function, right? So the derivative of this function is going to be the velocity function, right? So again, it's just the derivative of that function. So in other words, my velocity equals 0.08 doesn't go anywhere. The cosine function would become a negative sine function, so I'll throw that in parentheses so that we know we're multiplying, not subtracting, right, of 3.51 pi times t. But then because this sine function has an interior function within it, right, we'd have to do a chain rule, so we'd have to do the times the derivative of the inside of that function as well, so times 3.51 pi as well. And then cleaning this up a little bit, right, I've got my velocity equals, I'm going to multiply the 0.08 times this and then make that negative. So I end up, when I do that, when I take 0.08 times 3.51 pi, I get negative 0.2808 pi, and obviously I took that to a few decimal places, and then times sine of 3.51 pi t. Right, so notice here again, it should be a negative number, and that's perfectly fine, right? When we do the derivative of cosine, it is negative sign, so it should in fact be a negative function for us. So we do have that to work with. And then again, all I did was I multiplied the numbers that I could, and I left pi in there. So I left my pi in the answer. So then let's do this one more time, right? To find the acceleration function, once again, you could use the max acceleration, and there's a couple different ways we can find that. But I think it's really not that bad to just do a second derivative, right? The derivative of the velocity function. So to find my acceleration function, it's negative 0.2808 pi. Now the sine, the derivative of sine, becomes cosine of 3.51 pi t. And once again, I have to multiply it by the inside derivative as well. So times 3.51 pi as well. And so when I multiply then the negative 0.2808 times 3.51, I get my final acceleration equals negative 0.986 pi squared, and I am leaving the pi times pi as pi squared, and then cosine of 3.51 pi t. Right. So again, once I've established that position function, hopefully it's very easy to then find my acceleration and my velocity functions. Right. Even if I didn't find the maximum velocity first, I could just do the derivative and then work with it from there. So anyway, a good question to kind of close out this section. By all means, if you guys do have any trouble with this, or if you have any trouble with any of the other questions on this homework assignment, please don't just write them down, right? Don't just write your answers in, but come find me. This is an important section that we need to be pretty comfortable with.